Today, we are going to build Diffusion Model from scratch in just 50 minutes. You've heard the names, Stable Diffusion, DALLE, Midjourney. You've seen the incredible images they can create from just a few words of text. And let's be honest, it feels like magic. But it's not. It is a DDPM. What's that? A denoising diffusion probabilistic model. And the core idea behind it is surprisingly simple. It happens in 3 steps. Step 1. We destroy. This is called the forward process. We take a perfectly clean image and we systematically add noise, step by step, until only static remains. You can see it on the screen here, going from time step t equals 0 to 250 to 500, all the way up to t equals 1000, where it's pure noise. Step 2, we teach. We train a neural network to do one very specific thing: predict the noise that was added to an image. Look at this diagram. We take a noisy image, x sub t, we feed it into a UNet model along with its time step t, and we ask it to predict the noise that was added. The loss function? It couldn't be simpler. It's just the mean squared error between the actual noise and the predicted noise. And finally, step 3, we create. This is the reverse process. We start with a canvas of pure static, pure noise, and we ask our trained network to heal it step by step. As you can see, it goes from t equals 1000 down to 750 until at t equals 0, a clean new image emerges. So what's the entire secret to this? One Python file, about 150 lines of code, and we're going to walk through it right now. Don't worry about understanding every single line. This is just a high-level flyover. Here it is, diffusionmin.py. Part 1, the configuration. Our blueprint, all the settings like image size, channels, and how many time steps. Part 2, time embeddings. This tells the network where it is in the noising process. Part 3, the UNet block, the basic building block that processes images while knowing what time it is. Part 4, the UNet itself. This is our noise predictor. It looks at a noisy image and guesses what noise was added. Part 5, the forward process. A shortcut formula that lets us add noise to any time step instantly. Part 6, training. We show the network noisy images, it predicts the noise, and we compare to the truth. And Part 7, sampling. We start from pure noise and loop backwards, subtracting predicted noise until a clean image emerges. So, after all that, what will you master by the end of this course? You will master the forward process. You'll understand exactly how to destroy an image in one step using this formula. It's just a simple blend of the clean image and pure noise. You'll master the reverse process, how to heal an image step by step. You'll understand this formula, which looks intimidating, but it's really just a recipe for taking the current noisy image, x sub t, and producing a slightly cleaner version, x sub t minus 1. You will master the training objective, and it is brutally simple. The loss is just the mean squared error between epsilon, the real noise we added, versus epsilon theta, the noise our UNet predicted. And finally, you'll master the architecture, a UNet that knows what time it is. It takes a noisy image, x sub t, and the time step t as input, passes them through the UNet, and gets the predicted noise as output. 4 concepts, that's it. By the end of this, you will understand all of this, inside and out. All right, let's get building. Every complex project, whether it's a skyscraper or a neural network, it always starts with a blueprint, a plan that lays out all the critical specifications. In our code, this blueprint is a little class called Diffusion Config. Let's take a look. As you can see on the screen, it's a Python @data class. Don't worry too much about that. It's just a clean way to group a bunch of variables together. Think of it as a container for all the knobs and dials we can turn to control our model. So let's break this blueprint down. First up, we have dimensions and capacity. First, image size is 32. This is our canvas, 32 by 32 pixels. Why so small? Just for speed, so we can train this thing quickly. Next, in channels equals 3. That's for RGB color images. And base channels is 64. This is a big one. It controls the network's windows. Window, a larger number means a smarter, more powerful model, but it also means it's slower. Next, let's talk about time and duration. We have time emb_dim, which is the size of the time signal vector. The model needs to know where it is in the process, and this vector tells it. We've set it to 256. Then there's time steps, which we've set to 1000. This is the depth of destruction. How many steps does it take to go from a clean image to pure static? 1000. And finally, my favorite part, the noise schedule. This controls how fast we destroy the image. We have two key parameters here. First is beta start, which is 1e to the minus 4, or 0.0001, a tiny amount of noise at the very beginning. Then we have beta end, which is 0.02, a much larger amount of noise at the end. Let's visualize that. We linearly interpolate from our tiny beta start value to our much larger beta end value. So as you can see in this timeline, at time step 0, we're adding just a tiny bit of noise. But by the time we get to the end, at time step 1000, we're adding 200 times more noise. We go from a clean image to a slightly noisy one, to a medium noisy one, to heavy noise, until finally, it's pure static. And with that, our blueprint is defined. All the core parameters are set. Now it's time to build the first part of our machine, the forward process. All right, chapter 2. This is where we get into the math and the intuition behind diffusion. So what is the forward process? Simply put, we destroy the image. That's it. That's our only job in this chapter. We take a beautiful, clean image and we systematically, step by step, turn it into pure noise. So how do we do that? Let's look at the formula for a single step. Now don't be intimidated by the math. We're going to break it down. The formula says x sub t equals the square root of alpha sub t times x sub t minus 1 plus the square root of beta sub t times epsilon. Okay, let's unpack that. There are two main parts. First is the signal. That's the part with x sub t minus 1, which is just our image from the previous step. And alpha sub t is the amount of that image we decide to keep. Then we have the noise. Epsilon is just a fresh batch of random Gaussian noise. Think of TV static. And beta sub t is the amount of that new noise that we add. So we're keeping some of the old and adding a little bit of new static. So how do we build this formula? There's one simple but really important constraint. Alpha sub t plus beta sub t must equal 1. That's it. So if we decide to keep, say, 99.99% of the signal, that's our alpha, then our beta, the amount of noise to add, must be 0.0001. They always have to add up to 1. But here's the question you're probably asking. Why the square roots? Why not just alpha times the image and beta times the noise? Well, the reason is that the variances have to sum to 1. This is a subtle but critical point that keeps our pixel values stable. By squaring the coefficients, the square root of alpha squared is just alpha, and the square root of beta squared is just beta, we get alpha plus beta, which equals 1. This little trick prevents the image's energy from exploding or vanishing. It keeps everything nicely controlled. But there is a problem. A big problem. Iteration is slow. Look at this diagram. To get the noisy image at step 500, you have to start at step 0, calculate step 1, then step 2, then step 3, all the way down the chain. For a training step, that would mean doing 500 sequential operations. That is painfully slow. We can't build a model that way. We need a shortcut. And luckily, there's a beautiful mathematical property that gives us one. It's called the Gaussian property. I won't read the whole formula, but the key idea is this. If you add two sources of Gaussian noise together, you just get a new, bigger source of Gaussian noise. Their variances simply add up. This means we can merge 500 tiny noise steps into one big noise step. So let's derive that shortcut. Stay with me here. Step 1. We write out the formula for x sub 1, which is just our one-step formula starting from the original image, x sub 0. No surprises there. Step 2. Now we write the formula for x sub 2. And here's the trick. We subscribe the entire expression for x sub 1 right into this equation. When we expand that out, we get a term with the original image, x sub 0, and now we have two separate noise terms. This is where we apply the Gaussian property. We can combine those two noise terms into one. The slide shows the algebra. We take the variance from the first term, add the variance from the second term, a bunch of things cancel out, and we're left with a beautifully simple result, 1 minus alpha 1 times alpha 2. So our formula for step 2 simplifies down to this. X sub 2 equals the square root of alpha 1 times alpha 2 times x sub 0 plus the square root of 1 minus alpha 1 times alpha 2 times epsilon. And notice the pattern here. that product, alpha 1 times alpha 2, appears in both terms. And this pattern continues. For x sub 1, we use alpha 1. For x sub 2, we use the product of alpha 1 and alpha 2. For x sub 3, it's the product of alpha 1, 2, and 3, and so on. This gives us the final general formula, the shortcut. It says x sub t equals the square root of alpha bar sub t times x sub 0 plus the square root of 1 minus alpha bar sub t times epsilon. And that new symbol, alpha bar sub t, is just the cumulative product of all the alphas up to that point. Alpha 1 times alpha 2 times all the way to alpha t. This formula lets us jump from our original image at step 0 to any time step t instantly. Let's think about the intuition. Look at the signal part. As t gets bigger, say up to 1,000, alpha bar, which is a product of many numbers smaller than 1, gets really close to 0. The original image just fades away. Now look at the noise part. As alpha bar goes to 0, 1 minus alpha bar goes to 1. The noise completely takes over. So with this one formula, we can get the noisy image for any t, instantly. Okay, that's enough math. Let's code. Welcome to Chapter 3, the forward process code implementation. Our one and only target is to implement this formula, the shortcut. On the left, you see the input we need to calculate, alpha bar sub t, which is that cumulative product of 1 minus beta. And on the right, you see the output we want, the noisy image, x sub t, which is a mix of the original signal, x sub 0, and some fresh noise, epsilon. And again, just look at that beautiful property where the squared coefficients for signal and noise sum to 1. Perfectly balanced. So how do we do this in code? We'll break it into two main parts. Part 1, pre-computing the schedules. Since alpha bar sub t only depends on the time step, not the image itself, we can calculate all of its values just once when we create our diffusion object. It's way more efficient. Looking at the code here, inside the init method of our diffusion class, we'll set up everything we need. First, we define the variance schedule, beta sub t. We use torch.lineamized to create a tensor of evenly spaced values, just like you see in the example. It starts at a tiny value for beta 1 and grows linearly to a larger value for beta 1000. So a little noise at the beginning, more noise at the end. Next up, we need that cumulative signal, alpha bar sub t. This is a two-step process. First, we get alpha sub t, which is just a simple 1 minus beta. Easy enough. Then we compute alpha bar sub t using the magical torch.comprod function. This is perfect for our needs. You can see in the little example here, if you give it a tensor like 0.9, 0.8, 0.7, it calculates the cumulative product. First 0.9, then 0.9 times 0.8, then that result times 0.7. It's exactly the definition of alpha bar. So we pre-compute beta, alpha, and alpha hat, which is just our code name for alpha bar, and store them. Schedule's ready. Now for the shortcut itself. This function, which we'll call noise images, is the heart of the forward process. It takes two key inputs, x, which is a batch of our clean images, and t, which is a batch of random time steps, one for each image. Inside, we'll calculate the square root of alpha hat and the square root of 1 minus alpha hat, sample some noise, and combine them. But there's a small but crucial challenge we need to solve. The shape mismatch. Here's the thing. We need to multiply a single scalar value for each image, our alpha hat sub t value, by the entire image tensor. Our alpha hat's values for the batch have a simple shape of, well, batch, just a 1D list of numbers. But our images have 4 dimensions: batch, channels, height, and width. PyTorch can't just multiply these two shapes together directly. It wouldn't know how to align them. So how do we fix it? With a clever little reshape trick. Look closely at the code again. After we index into our schedule with t, we add this strange looking slice, colon, comma, none, comma, none, comma, none. What on earth does this do? It adds new, empty dimensions to our tensor. It takes our old shape of batch and transforms it into batch by 1 by 1 by 1. And now, PyTorch's broadcasting rules can kick in. It automatically stretches that 1 by 1 by 1 to match the 3 by 32 by 32 of our image for the multiplication. Problem solved. Okay, with that reshaping handled, the rest is super straightforward. We sample our noise, epsilon, using torch.randn_like of x. This is a fantastic function that creates Gaussian noise with the exact same shape as our input images. No guesswork needed. Then we just apply the formula. sqrt aliza hub.hand times x plus sqrt 1min.initheb times epsilon. Finally, notice we return both the noised image and the original noise, epsilon, that we used. This is critical. That noise, epsilon, is our ground truth. It's the target that our UNet model will be trained to predict. So let's put it all together and summarize. Here is the complete forward process. In our init method, we pre-compute the schedules, beta, alpha, and alpha hat. Then, in our noise slew function, we take a batch of images x and time steps t. We look up the right values from our pre-computed schedules, reshape them for broadcasting, sample some fresh noise, and combine everything to get our final noisy image. You can see all the variable shapes in this table here. Everything lines up perfectly. And that's it. Forward process complete. We can now generate basically infinite training data on the fly. We can take any image from any dataset and corrupt it to any time step instantly. But here is the real question. We know how to add noise. That was the easy part. But how do we reverse it? Welcome to the reverse process. The goal is simple. We need to reverse the arrow of time. As you can see in this diagram, we're going to start with pure static, and then, step by step, we will remove noise to get a slightly less noisy image, and we'll keep removing noise until we're left with a clean, coherent image. But here is the fundamental challenge. Remember the forward process? The formula x sub t equals the square root of alpha sub t times x sub t minus 1 plus the square root of beta sub t times epsilon. That was easy. We just add a little bit of Gaussian noise at each step. Simple. The reverse process, though, that's a different story. Given a noisy image, x sub t, what was the previous image, x sub t minus 1? It's hard. In fact, it's more than just hard. Mathematically, it's intractable. You can't just subtract the noise because you don't know which random noise was added. Calculating this probability directly would require using the entire dataset for every single step. It's computationally impossible. So what do we do when something is intractable? We do what we always do in deep learning. We approximate. We're going to train a powerful neural network to learn this reverse step for us. Now for the first big question. What should this network predict? The obvious answer seems to be predict the slightly less noisy image, right? Wrong. We are not going to predict the image. Instead, we predict the noise. But why? Why predict the noise? This feels totally counterintuitive. Well, take a look at our shortcut formula again, the one that lets us jump to any time step t in one go. X sub t equals the square root of alpha hat sub t times x sub 0 plus the square root of 1 minus alpha hat sub t times epsilon. Think about what we have here. We know this part, x sub t. That's the noisy image we feed into our model. Our model is going to predict this part, the noise, epsilon. And if you know x sub t, and you have a good guess for epsilon, you can just do some simple algebra, rearrange the formula, and solve for this, the original clean image, x sub 0. It's an absolutely brilliant reframing of the problem. So this is our model's entire job. We call it the noise predictor, or epsilon theta. As you can see in this diagram, it's a model, in our case a UNet, that takes two inputs, the noisy image, x sub t, and the current time step, t. And it has one job and one job only, to spit out its best guess for the noise that was added to that image. Our model, epsilon theta, operating on x sub t and t, will try to approximate the real noise, epsilon. This all comes together beautifully in the training loop. Let's walk through this diagram step by step. 1. We pick a real, clean image, x sub 0, from our dataset. 2. We pick a random time step and add a random amount of noise, epsilon, to get our corrupted image, x sub t. This epsilon that we just added, that's the truth. We save that. 3. We take our noisy image and the time step and feed them into our neural network. The network looks at it and makes a guess. It predicts some noise. And finally, step 4, we compare. We take the network's guess and compare it to the truth, the actual noise we added back in step 2. From that comparison, we calculate our loss, which tells the model how to get better. And what does that comparison look like? The objective function is beautifully simple. It's just the mean squared error, or MSE. As you can see in the formula, the loss, L, is just the squared difference between the actual noise, epsilon, and the predicted noise from our model, epsilon theta. That's it. 1. Take the actual noise. 2. Subtract the predicted noise. 3. Square the difference. The entire complicated, mind-bending process of training a diffusion model boils down to a simple guessing game. We're just showing the model a noisy image and asking, hey, what noise did I add? And we train it to get better and better and better at that one simple task. Okay, we have the theory. We have the core insight. We understand the objective. Let's build the training loop. You might be thinking this is going to be some massive, complex piece of engineering. Well, what if I told you the entire training loop is just 4 lines of code? Seriously, that's it. Let's build it. First, we'll need a tiny helper function. It's called sample time steps. As you can see in the code, def sample time steps self, n, its whole job is to generate a list of random integers. It uses torch.random. N is just our batch size, say 8 images. Low equals 1 is the start of the noise schedule, and high equals 1000 is the end. Super simple. But why random? Why not do things in order? Well, let's consider 2 options. Option A, we could train on all the steps. For every single image, we could run it through time step 1, then 2, then 3, all the way to 1000. What's the result of that? You'd have 1000 forward passes for just one gradient update. It would be way too slow. So we use option B, random sampling. For each image in our batch, we just pick one random time step. That's it. The result? Over thousands of batches, the model eventually sees all the different noise levels. It learns to be robust. And best of all, it's 1,000 times faster. Okay, let's look at those 4 magical lines. This is the forward method, the heart of our training. Here's the entire thing. Def forward, self, x. 4 simple lines. Let's break it down, one by one. Step 1, time. The first line is t equals self.sample time steps of x.shape at index 0. All that's doing is calling our helper function to get a random time step for each image in the batch. Remember, x.shape at index 0 is just the batch size. So if we have 8 images, t will be a little list of 8 random numbers, like 150, 27, 843, and so on. Easy. Step 2, data generation. The next line is x_t, noise equals self.noiseImages of x, t. This is where we use our forward process shortcut from the previous chapter. We take our clean images x and our random time steps t, and we generate our training data on the fly. We get back 2 things, x_t, which is our noisy image that will be the network's input, and noise, which is the pure noise we added. That noise is the ground truth. It's the target our model is trying to predict. Step 3, the prediction. Now we get to the fun part. Predicted node equals self.model of xt, t. Here, we just ask the model, hey, how much noise is in this image? We give it the noisy image xt, and critically, we also give it t, the time step, so the model knows the intensity of the noise it should be looking for. And don't worry, we're going to build this self.model in the very next chapter. Step 4, the judge. The final line is return f.mse loss of noise, predicted noise. This is where we judge the model's performance. We compare the real noise, the ground truth, against the predicted noise from our model. We use a simple mean squared error, which calculates the error pixel by pixel. The lower the loss, the better the model is at healing the image. And that's it. That's the entire loop. Now, for those of you who love tracking your tensor shapes, here's a quick reference. You can see the clean images x, the noisy input xt, the target noise, and the predicted noise all have the exact same shape, batch size, by 3 channels by 32 by 32. The time steps t is just a vector with a value for each image in the batch. And all of this gets crunched down into a single scalar value, the loss, which we use to make the model better. So we have the loop, we have the data generation, we have the loss function, we're pretty much there, but one mystery remains. The big black box in our code. What is self.model? We need a model, a noise predictor, that can look at a noisy image and tell us exactly what noise was added. The architecture we're going to use for this is called a simple UNet. So what's its job? It's incredibly simple. The input is a noisy image, and the output is the pure noise that was added to it. That's it. That's the entire task. Image in, image out. Whenever you have a task like this, where the input and output are both images of the same size, there is one architecture that absolutely dominates. We need a UNet. And here it is, the visual blueprint. It's called a UNet because, well, it's shaped like a U. On the left side, the data goes down in what we call the encoder, and on the right side, it comes back up in the decoder. You can see we start with our 3 by 32 by 32 input image. We squeeze it down, 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 getting smaller and smaller until we hit this tiny little bottleneck at the bottom, and then we expand it all the way back up to its original size. And you see those little lines jumping across the U? Those are the secret sauce. Those are called skip connections. So what are these two sides actually doing? Well, the encoder, as it goes down, compresses the dimensions. It sacrifices the little details to understand the big picture, the context. It's trying to answer the question, what is in this image? Is it a car? A face? A dog? Then, the decoder does the opposite. As it goes up, it expands the dimensions. It tries to reconstruct the image and restore all that fine-grained detail. It's asking, okay, now where do all the pixels go? But here's the challenge. That compression process, it loses information. A lot of detail gets thrown away on the way down. So how do we get it back? The solution is those skip connections. I like to think of them as a cheat sheet. We basically teleport the high-resolution features directly from the encoder and give them straight to the decoder. Look at this diagram. An encoder layer processes the image, but before passing it down, it makes a copy of its work. Then it just pastes that copy directly over to its partner layer on the decoder side. It's a perfect cheat sheet, giving the decoder both the high-level context from the bottleneck and the fine-grained detail from the side. Okay, let's see how this all translates to code. This is the forward method, the complete journey our data takes through the UNet. First up, the setup. The first line is t equals self.time_mlp of time step. All this does is take our simple integer time step, like 542, and convert it into a rich vector embedding that the network can actually understand. More on that later. Then, x equals self.conv0 of x. This is an initial convolution that just projects our image from 3 RGB channels into a much bigger feature space, in our case, 64 channels. Next, the encoder. We loop through a series of downsampling blocks. And here is the critical step of the encoder. Residual info.append of x. With every step we take down the U, we save the output. We append it to this list. This list, residual input, is our cheat sheet. Now for the decoder. We've hit the bottom of the U, and we're on our way back up. In each step of our upsampling loop, we first do a pop. This grabs the last cheat sheet we saved from the matching level of the encoder. Then comes the magic. Torch.cat. This is the skip connection. We literally glue the old features from our cheat sheet right next to the new features from the decoder. Now you might be wondering, why cat instead of add? Why concatenate them instead of just adding them together? Well, addition is destructive. It merges the information, and the network can't tell what was context and what was detail. You start with 2 tensors of 256 channels, and you end with just 1. But concatenation, it just stacks them side by side. As you can see in the diagram, you start with 2 tensors of 256 channels, and you end up with one big tensor of 512 channels. Both sets of information are preserved. We're letting the next layer decide for itself how to mix them. It's way more powerful. Finally, the output. After coming all the way back up the U, we have a final output convolution. This simply maps the 64 feature channels back down to the 3 RGB channels we need for our final image. The result is a tensor with the exact same shape as our input, batch by 3 by 32 by 32. This is our predicted noise. And for those of you who love tracking your tensor shapes, here's a quick reference for that entire journey. You can see the shape as it starts at the input, gets compressed by the encoder while the channels grow, hits that bottleneck of pure context, and then expands back up in the decoder, getting bigger spatially while the channels shrink. It's a beautiful, symmetrical process that ends right where it began, giving us our final noise prediction. All right, we've seen the skeleton of our UNet. Now it's time to look at the organs, the real guts of this thing. We're going to master the 2 most important components today. First, time embeddings. This is how we convert a simple time step, like t, into a rich vector the network can actually use. And second, the block. This is the workhorse that does all the heavy lifting, convolutions, time injection, and all the upsampling and downsampling. As you can see on the slide, there's a fair bit of code for each, but don't worry. We're going to break down exactly what's going on piece by piece. Let's start with time. Part A, encoding time. So here's the problem. The time step t is just a scalar, a single number. And if you just feed a single number like 500 into a neural network, that's a really weak signal. It doesn't give the network enough information to work with. The solution? Embeddings. We take that weak scalar and we transform it into what I like to call a vector fingerprint. Something like this vector here. Now that is a rich signal. It has texture. It has nuance. The network can learn complex patterns from this. So how do we create this unique fingerprint? Well, the intuition is actually pretty cool. We use waves. Think about it. If you combine a high-frequency wave, like the green one here, with a low-frequency wave, like the red one, you get a completely unique combination of values at every single point in time. It's a signature. Let's look at the code that does this. This is the sinusoidal position embeddings module. The key part is how we generate the different frequencies. We use a formula that was adapted from the original transformer paper. I won't read out the math, but just know that it uses a log and an exponent to create a smooth, geometrically spaced sequence of frequencies. This is just for numerical stability. Now for the mixing part. Once we have our frequencies, the process is simple. First, we multiply our time step t by that whole vector of frequencies. Then we apply a sine function to the first half of the results and a cosine function to the other half. Finally, we just concatenate them together. And boom, our output is a rich vector with the shape batch by dimension. And if you want to go deeper on this, check out our video on rotary position embeddings, or ROPE. It's the same core idea. Okay, part B, the block. This is the true workhorse of the UNet. When you look at this diagram of our UNet, every single one of these boxes is a block. The input goes into a block, which downsamples it, then another block, all the way down. Then we hit the bottleneck and come all the way back up through more blocks. We have 4 blocks going down and 4 blocks coming up. That's 8 blocks in total, all sharing the same fundamental architecture. So let's dissect one. Here's the anatomy of a single block. The image features from the previous block come in as input X. They go through a convolution, a group norm, and a GELU activation. But in parallel, the time embedding comes in. It gets projected by a linear layer, and then, here's the key part, it gets added to the image features. This is the time injection. It happens right between the 2 main convolutions. After that, the combined result goes through a second convolution stack, and then finally an up or downsampling transform before heading to the next block. Let's check out the code that sets this up. This is the init method. The first thing to notice is self.timemlp. This is just an nn.linear layer. So why do we need this? Well, we have to add our time vector to our image tensor, but they have different dimensions. This is a dimension mismatch problem. The solution is this linear layer. It takes the time embedding, which might have a dimension of, say, 32, and projects it to have the same number of channels as the image, like 64 or 128. It's just a simple matrix multiply. Output equals input at weights plus bias. Problem solved. Next, look at this if-up logic. This is for handling the skip connections. If we're on the upsampling path of the UNet, up will be true. That means our first convolution needs to handle twice the number of input channels, because we just concatenated the features from the skip connection. And the transform layer becomes a conv transpose 2D to upsample the image, making it bigger. So what is a conv transpose 2D? Honestly, the easiest way to think of it is as stamping. Imagine your input is just 1 pixel with a value of 5, and you have a learned 2x2 kernel. The transposed convolution literally stamps that kernel onto the output canvas, scaled by the input pixel's value. So a 5 becomes a 5, 10, 15, 5 region. Each input pixel paints its own little kernel onto a bigger canvas. It's how we grow the image back to its original size. Okay, let's look at the forward method, where the data actually flows. The time injection happens in just a few lines. First, we project the time embedding t through our time MLP layer. That gives us a vector with the right number of channels. Second, we reshape it. We add 2 dummy dimensions for height and width. This is a classic broadcasting trick that turns a vector of shape, say, batch by channels, into a tensor of shape, batch by channels, by 1 by 1. And that sets us up for the merge. H equals h plus time.emp. This simple addition is the most critical step in the whole block. Because we reshape the time embedding, PyTorch automatically broadcasts it, adding that same time signal to every single pixel in the feature map. This simple addition shifts the activations of every pixel based on the noise level. This is how the network finally knows when it is. It knows if it's at a noisy step or a clean step and can adjust its strategy. It's brilliant. For reference, here's a table showing how the tensor shapes change as they move through the block. The input x comes in, the time t comes in, they get processed, they get merged, and the output has a new height and width, either halved for downsampling or doubled for upsampling. And with that, the architecture is complete. We have built all the pieces. We have a brain. Now, let's dream. Now comes Chapter 8, Generation and Sampling. We're going to cover the math and the intuition behind how we go from nothing to a beautiful image. The goal is simple. We want to go from chaos to order. As you can see in this diagram, we start with x sub t, which is just pure static noise. And then, step by step, we patiently walk backwards, transforming it into something less noisy, and then a little less noisy, until finally, after 1,000 steps, we arrive at x sub 0, a clean, coherent image. But this raises a question. To start this reverse journey, we need a starting point. And to get that starting point, we're going to use a very, very clever trick. Here's the trick. At the very end of the forward process, at time step t equals 1,000, remember that alpha bar sub t is approximately 0. What does that mean? It means the signal from the original image is gone. It has been completely washed out by the noise. The output of the forward process is statistically identical to just random Gaussian noise. So, what do? We just sample random noise. We don't need a real noisy image to start with. We just call x sub t equals torch.randn, and that's our starting block. Simple as that. Now for the core insight. Recall the forward shortcut formula from a few chapters ago. It said that x sub t equals the square root of alpha bar sub t times x sub 0 plus the square root of 1 minus alpha bar sub t times epsilon. Now think about this. Alpha bar sub t is just a number we pre-computed. Epsilon is the noise we added. And x sub t is the noisy image we have right now. If we know what epsilon is, thanks to our amazing UNet, we can just rearrange this formula algebraically and solve for x sub 0. As you can see in this formula here, our predicted x sub 0 is just a function of the current image x sub t and our model's noise prediction, epsilon theta. This is huge. Predicting the noise is the same thing as predicting the original clean image. So wait, why not just jump straight to x sub 0? We have the formula. Why go through all 1,000 steps? Well, because our guess is imperfect. Especially in the early stages when the image is mostly noise, our UNet's prediction for epsilon theta is just a rough estimate. A single big jump would lead to a blurry, averaged out mess. So, don't jump, walk. We take small, careful steps, refining our prediction each time. And this is the recipe for how to walk. This formula here is the famous DDPM sampling step. It tells us exactly how to get from our current image, x sub t, to the previous, slightly cleaner image, x sub t minus 1. Now, I know it looks intimidating. All these alphas and epsilons and sigmas, but the intuition is actually quite simple. Let's break it down into 3 easy steps. Step 1, highlighted here in red, is to denoise. The core of the operation is right here, x sub t minus some scaled version of epsilon theta. We take our current noisy image, we ask our UNet to predict the noise in it, we scale that prediction using those alpha terms we pre-computed, and we subtract it. That's it. We're literally carving the noise out of the image. Step 2, in green, is to correct the scale. Look at that term out front, 1 divided by the square root of alpha sub t. Why is that there? Well, remember in the forward process, at every single step, we multiplied the image by the square root of alpha sub t, which slightly shrank all the pixel values. So now, in the reverse process, we have to do the opposite. We divide by the square root of alpha sub t to bring the values back up to where they should be. It's just a simple correction. And finally, step 3. In cyan, we inject a little chaos. After all that work, we actually add a little bit of new noise back in. That sigma sub t times z term, that's what that is. Z is just fresh random noise, and sigma t is a small predefined value. But why would we do that? It prevents the model from collapsing into a single, boring, averaged out image. This little injection of randomness adds texture, detail, and variety to our generations. It's what makes the images feel alive. A quick note though, we only do this for t greater than 0. At the very last step, we don't add any noise back in. And that's it. That's the entire generation process. We just put those 3 steps into a loop. As you can see in this diagram, we start with random noise, x, at step 1000. Then we ask, is t greater than 0? Yes, it is. So we apply the recipe. Then we update t to be t minus 1, and we go back to the top. Is t greater than 0? Yes. Apply the recipe. Update t. Over and over and over again for 1,000 steps, until finally t is not greater than 0, and we exit the loop with our final clean image, x sub 0. The math is defined. The logic is set. Let's go code the loop. Welcome to Chapter 9, Generation and Sampling, the code implementation. Okay, let's get our hands dirty. What you're looking at here is the entire sampling loop. This is the sample method inside our diffusion class. It looks a little dense, I know, but here's the thing. It's just a direct, line-by-line translation of the math we just learned. We're going to dissect this function step by step, and you'll see how every single line has a purpose. Let's begin. Step 1. Setup and chaos. First things first, we need to prepare our environment. We start with the decorator @torch.nograd. This is a huge optimization. It tells PyTorch, hey, we're not training right now, so stop tracking gradients. This saves a ton of memory. Next, self.model.eval. This officially puts our UNet into evaluation mode, freezing layers so they behave correctly for inference. And finally, the most important part, x equals torch.randn. This is our canvas. We are creating a batch of images filled with pure, unstructured Gaussian noise. This is our starting point, our x sub t. Step 2. Time travel. Now for the main event, the reverse loop. Look at this line. For I in reversed range 1 to 1000. This is where we literally travel backwards in time. We're starting at step 999, then going to 998, all the way down to 1. Inside the loop, we create t, a tensor of the current time step I. We're essentially preparing a question for our model for every single image in the batch. The question is, hey UNet, for this image, at this specific time, what does the noise look like? Step 3 is to gather our ingredients. Remember all those alpha and beta values we pre-computed? It's time to use them. For the current time step t, we simply retrieve alpha, alpha hat, and beta from our pre-computed schedules. Now this is critical. See those nuns being added to the dimensions? That's reshaping the tensors. We're taking a value for the batch and expanding it so it can be broadcast across the height, width, and channel dimensions of our image tensors. It's a small detail that makes all the math work perfectly. Step 4. Inject a little chaos. This is the Langevin noise we talked about. We need to add a little bit of new noise, Z, back into the image at every step. But here's the catch. We only do it for most of the steps. We have a simple if statement. If I is greater than 1, noise is a fresh tensor of rand_in like x. But if we are on the very last step, where I equals 1, we set the noise to be all zeros. Why? Because we want the final result to be a perfectly clean image. The chaos has done its job. It's time for the final reveal. And now, step 5, the formula. This single line of code is the diffusion model's creative spark. And what's so beautiful is that it's a direct translation of the math. Let's look. The code says 1 over alpha dot square root. And on the right, you see the math, 1 over the square root of alpha t. The code has x minus a term, and the math has x sub t minus a term. The code uses our predicted polarization from the model, which maps directly to epsilon theta in the formula. It's literally the same thing. We take our current image x, subtract the predicted noise, scale it, and then add back that little bit of Langevin chaos. This one line is repeated almost 1,000 times to create art from noise. We're almost there. Step 6, the final polish. After the loop finishes, our image tensor x is in the -1 to 1 range, which is great for training, but for display, not so much. We need to normalize it. First, we clamp the values between -1 and 1, just to fix any tiny numerical errors that might have crept in. Then, we add 1, which shifts the range to 0 to 2. Finally, we divide by 2, scaling the range perfectly to 0 to 1. And just like that, our tensor is ready to be saved as a PNG or a JPEG. It is a masterpiece, born from chaos, guided by math. We've reached the end. You've done it. You have officially built a diffusion model from scratch. We started this journey with something that looked like, well, magic, a complete black box. And we made a promise that by the end, we would dissolve that magic into pure, understandable, elegant engineering. And that is exactly what we did. Let's zoom out and look at the full picture. This diagram shows the complete life cycle. We take a real image, we run the forward process to methodically turn it into pure noise. Then, in the middle, during training, we teach a model to predict that noise. And finally, in the reverse process, we use that trained model to turn new noise into a brand new image. Let's break down those 3 pillars one last time. First, pillar 1, the forward process. This is all about destruction. We had a variant schedule, beta t, that controlled the rate of noise. We figured out the shortcut that lets us jump to any time step t instantly. And it was all governed by this one beautiful formula you see here. X sub t equals the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon. Simple deterministic destruction. Next, pillar 2, the training process. Here we teach. The task was simple. Predict the noise epsilon. Our tool was the UNet, supercharged with those special time embeddings. And the objective? The goal of our training? Just minimizing the squared difference between the real noise, epsilon, and the noise our model predicted, epsilon theta. That's it. A straightforward, supervised learning problem. And finally, pillar 3, the generation process. This is where we create. We start with pure chaos, a tensor of random noise called x sub t. Then we loop. Step by step, removing a little bit of the predicted noise each time. And the result? We transform that chaos into order. A beautiful new image, x0. The recipe for this creation? It's that sampling formula we just implemented. X sub t minus 1 is simply a function of our current image, x sub t, minus a scaled version of the noise our UNet predicts. So after all this, you might be asking a very important question. Is this stable diffusion? Yes and no. Let me explain. The engine you built is the same, but there are two key differences. As you can see in this table, our model operates in pixel space, which can be slow and heavy. Stable diffusion operates in what's called latent space, which is fast and compressed. Second, our model is unconditional, meaning it just generates random images. Stable diffusion is conditional, guided by text prompts. So what is this latent space? Look at this diagram. Instead of running the diffusion process on a big 512 by 512 image, Stable Diffusion first uses an encoder to squish it down into a tiny 64 by 64 latent representation. Then, it runs the exact same diffusion loop you built, but on that small, compressed data. It's so much faster. Finally, a decoder blows the result back up into a high-res image. The core process is identical. Okay, and what about conditioning? How do we get from random images to following text prompts? It's all about giving the UNet a little extra help. As you see here, we take a text prompt, like an astronaut riding a horse, and we feed it through a model like Clip to get text embeddings. These embeddings, which capture the meaning of the text, are then fed into the UNet at every single step of the denoising process, usually with a mechanism called cross-attention. This guides the UNet's predictions, forcing the final image to match the prompt. But here's the key takeaway. The engine, the core logic of destroying and then recreating an image by predicting noise, is identical. The black box is now open.